Now, chapter 18, it's going to be standing waves. And we'll talk about standing waves in strings and pipes. So the strings would be like the physics and acoustics of the string instruments. So right, what's going to happen in the string instrument is that you plug one end of the string, right? Something like this. Physics of instruments, right? So you plug one end of the string, and then you put your finger here, and the other end of the string is taut here, right? So then it makes a certain frequency, it vibrates at a certain frequency, right? So we want to say, what are the allowed frequencies given the length of the string and the properties of that string, the mass density of that string, okay? So usually for those cases, you're going to have the two ends of the string are going to be a node. That means it's going to be destructive interference. So that means they're not allowed to vibrate up and down. Right, so this is node, that means destructive interference happens. Then you've got pipes, which is the physics of wind instruments, or brass instruments, or all of those things, clarinet. So then you have pipes with both ends closed. So this is closed, closed. So then when it's closed, that's going to act like the stringed instrument with node, node, node. This is node, node. So the physics of this is exactly similar to how the stringed instruments are. Then you have open and open, 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 which means this is antinode, 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 antinode. But it ends up that it doesn't matter as long as this is antinode, antinode, the physics of it is the same as being node and node, right? So they make the same fundamental frequencies and harmonics as do these instruments make. The one that's different is when one end is closed and the other end is open. So then you have node and antinode combo. Okay, so then you have here closed and open, and then you have node and antinode. Okay, so then the physics of this is different than this. So this one and this one and this one is the same. Okay, so the way to kind of start out this topic of standing waves is to discuss what happens to a traveling wave as the traveling wave goes and meets a boundary. Remember, we talked about that topic all the way back in chapter 16. And so, okay, it goes and it meets a boundary, and it depends what happens at the boundary, right? There is some transmission and there's some reflection. In our case, we're going to assume that the boundary is a fixed boundary, so that all the energy reflects, right? All of the energy reflects. And then so we discuss here what happens to the incoming wave and then the reflected wave. So what is the physics of that? So then we're gonna say y1 is the incoming wave, a sine of kx minus omega t plus phi, right? And then y2 is a sine of, well, since it's basically reflecting back to the same medium, the k doesn't change and the omega doesn't change, except that the wave is traveling to the left, right? Plus omega t plus omega t plus phi. Well, for now, let's just do it this way. Let's not focus so much on the phi, but let's just do the physics of what happens when a wave is coming and another wave of the same frequency and wavelength is traveling backwards. In other words, we're focusing more on what's happening sort of in the middle, not so much at the boundary. Then we'll do the boundary conditions. So it's, what happens to the physics of a wave that's coming and another wave that's coming the other way, and they meet, right? And if their amplitude is the same, which they will be, because we're assuming all the energy is reflected back, right? So their amplitude will be the same. And of course, their K and W will be the same. So the only thing that's changing is their direction. So then we add those two waves. Y total is a sine of kx minus omega t plus a sine of kx plus omega t. Now we did this the other day on Monday, but in that case we were analyzing something slightly different. We had a speaker and another speaker, and then we had a traveling wave, and we have the traveling wave, and we wanted to know how those waves interfere. So that's a slightly different topic, right? Here we're still doing interference, but the waves are kind of meeting each other, going in opposite directions. In that case, we did something like this. Y total is a sine of kx minus omega t. So it's kind of nice to put them side by side to see how the analysis is different. Plus a sine of kx minus omega t. And then in that case, we were focusing on the fact that by the time they get there, they're off phase from each other because they've traveled different distances. You see? Here we're not focusing on that. We're just saying some random waves that are coming back and they happen to be in phase, but they're traveling in opposite directions. Okay? So in that case, we did a sine kx minus omega t plus phi 1 plus a sine of kx minus omega t plus phi 2. Okay, then we use this trig identity, right? So let's always remind ourselves of that identity. It's going to be 2 sine of a minus b over 2 cosine of, and now I always forget, is this sign a plus or is it minus? And cosine of a plus b over 2. So how was the identity? One of these was a plus, the other one was a minus, right?
I think cosine is minus.
Okay, cosine is minus. So in other words, if the sign here is plus, this one gets a plus. The sine gets a plus, but the cosine gets the opposite sign. Let's remember it that way. So in that case, we have what ended up happening. So if we apply this, if we apply this identity to that, so then we have here 2, and then the amplitude is a, and then we have here sine of, and then when we add them and divide by 2, you end up getting this adds to this adds to this, then you just basically double. And you divide that by 2, so you just end up getting itself again. Plus, then you have here phi 1 plus phi 2 over 2. Okay, then when you do the cosine, it ends up that this cancels this, and then you end up getting what? This and this and this and this cancel itself. Then you just have here phi 1 minus phi 2, which is delta phi over 2, right? Then the whole day we talked about what does that mean. You know, we focused on the rest of the time on 2a. So this is cosine of delta phi over 2 sine of kx minus omega t plus phi 1 plus phi 2 over 2, right? Then we talked about this thing is the net amplitude of the wave, right? So then the topic starts evolving, saying, okay, so then what are the conditions for these two waves to get there and meet each other such that they constructively interfere, right? So then we want this thing to be equal to the maximum possible that it can be, which is 2A. That's complete constructive interference. I see. Of course, if it's something other than 1, maybe cosine of delta phi over 2 is let's say 0.8. Well, then it's not complete constructive interference. It's somewhere between destructive and constructive. But we're focusing on complete constructive, which means they meet there exactly in phase, and the amplitude becomes 2A, right? And then the other one is destructive interference, which means 0. Destructive interference. So it's kind of nice to review this while we've already done it, just to really have it down, you know. And then you say, okay, what is the condition for that? Well, then you can say delta phi over 2 is equal to what? In order for this to be 1, delta phi over 2 needs to be 0, right? Well, when is cosine 0? Then you say cosine is 0 every time that the angle is pi over 2 or 3 pi over 2, right? Doesn't make sense. Hold on. It should be. No, not sorry. I don't want it to be 0. I want it to be 1. What am I saying?
1. That's okay.
1 or negative 1.
0.
Yeah. So then you need to be what? 0, pi, 2 pi, 3 pi. So then you say here, this is going to be 0, pi, 2 pi, 3 pi. Then you give that some kind of generalization. So we said the generalization is n pi, where n is 0, 1, 2, 3, so on and so forth. So that means delta phi 2n pi. That's the condition for the waves to behave. Yes. Yeah, it's the fourth sensor. It's probably yeah, look for fourth sensor. Okay, so then the next thing that we did was to say, okay, well, how do we relate the phase angle, the difference of the phase angle of this wave to the phase angle of this wave? Well, how do we relate that to the path, the distance that they traveled, right? So then I can say, well, the distance from here to here is R2, and distance from here to here is R1. That causes their phase angles to be off, right? So then we did delta R over lambda is delta phi over 2 pi, and we said that's a general relationship. So if the distance between them is off by a certain distance, we divide that by the wavelength of the wave. That causes their phase angle to be off by a certain radians over 2 pi. So in other words, if delta R is multiples of wavelength, then delta phi will be n integer multiples of 2 pi. So this is a general relationship between dr and d phi. Then we apply this to this scenario. We say, okay, d phi is equal to what? D phi is equal to 2 pi, so that we can write it as d phi is 2 pi dr over lambda, right? Once you find this condition, which comes from here, right? Then you put d phi is 2 pi delta r over lambda. Then you say, okay, pi 2 delta r is equal to n lambda. So that was the next thing we went to, and we said, okay, if the distance is integer multiples of wavelength, then we have constructive interference, right? Then we label this central max, first order max, second order max, and so on. So if you put a screen here, the central max will occur right in the middle. Then first order max, second order max, and so on. Then the next thing we said, okay, what are the conditions for delta phi to be for the destructive interference to occur? So then we have here delta phi over 2 is going to be pi, 3 pi over 2, right? Pi over 2, 3 pi over 2, 5 pi over 2. Then that will cause it to have 0, right? Complete destructive interference. And then you find the formula to express that. I think the formula that we used was what? The n plus half pi, right? Is that right? Where n is, or is it n is minus 1?
Minus.
Because I don't want n equals 0 to be a, I prefer not to use n is 0, right? So you can say, I'm going to start with n is 1 because there should not be a central min, right? So it's better to say n is 1, 2, 3, 4, da 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 da. And then this is going to be, then you check to see if this gives you that, right? So then you have 1 minus half, by, okay, that works. 2 minus half, that's 3 halves. 3 minus half, that's 5 halves. Okay, so then once it works, then you can call these guys first order min, second order min, right? Then you use the general relationship. Then you can say delta phi over 2, right? Delta phi over 2 is going to be pi delta r over lambda. Okay, so that means the difference of the path lengths traveled by the waves needs to equal half integer multiples of wavelengths for them to have complete destructive interference. Okay, good. So now how do we relate this to what we're going to do now? Well, we're going to have waves, instead of concentrating on their phase angle, we're going to have waves traveling in opposite direction. Okay? And we want to see how they add up. So 2a cosine of what? Remember, you subtract when you do the cosine, because it's opposite, right? So when you subtract kx minus omega t minus kx plus omega t over 2, right? So I'm again using that thing. So now we're doing the same procedure as we did here, right? Then we're going to do sine of kx minus omega t plus kx plus omega t over 2, right? So once you see this together, now you should be able to do it in your sleep, derive all these things, right? Some of the similar kind of things are going to occur, but it's going to be also quite different. There are some similarities and differences. Okay, then you have your 2a cosine of, so now here the kx cancels the kx, omega t minus omega t, So now it's going to have negative 2 omega t over 2. Sine of, then the omega t cancels the omega t, then you're going to have 2kx over 2. Okay, so then what is that? The 2 cancels the 2, the 2 cancels the 2. So you just end up getting a much different looking total y, right? 2a cosine of negative omega t. I think cosine is an odd function, is even, well, yeah, it's an even function, right? So cosine of negative omega t is the same as cosine of omega t, right? Because cosine of 20 is the same as cosine of negative 20. Right, so then it's just going to be cosine omega t sine kx. Okay, so now here comes the big bombshell. The combination of two traveling waves meeting each other in the opposite direction is no longer a traveling wave. That's the big bombshell. This is not a traveling wave. Why? Because in order to have a traveling wave, it needs to have this format, right? In other words, under the same trig function, you need to have a position function and a time function, right? And then the velocity of that wave is going to be what? Omega over k, right? As we studied in chapter 16. That means that's a traveling wave. The energy of the wave is propagating from one end to the other end. As the wave particle is going this way, this is a transverse traveling wave, right? Transverse. So the propagation of the wave is this way, up and down. How should I say it? The elements of the wave just go up and down, but the energy of the wave travels this way, you see? That's the nature of a traveling wave. But then what the heck is this? Here you don't have the kx and the omega t under the same trig function. Well, it's called a standing wave. Standing wave.
I have a question. Where is that formula coming from? Y total is equal to a sine kx minus omega t. Where did phi go?
Well, because I'm focusing not so much on their phase angle as I am on.
You just assume it's zero.
If we included the phi, would it make a huge difference? Let's see. If we included the phi, like you're saying, let's include a phi 1 and phi 2. Would that make a huge difference if we include that?
Right.
What would happen? You would have kx phi 1, so you would have a phi 1 and you would have a phi 2.
Yeah.
And phi 1 minus phi 2.
Yeah, we could generalize it. Let's say they have the different phase angle. Then you would end up with, here you would end up with phi 1 minus phi 2 over 2, right? So the more general result would be what? So negative omega t minus omega t, so that'll be negative 2 omega t on the top, then plus phi 1 minus phi 2, right? Over 2. Right?
Why is it like positive omega t and negative omega t?
Whatever, I mean, over here, what did we do?
Like both.
Plus phi 1 plus phi 2. It just, you could put anything here. You could put plus phi 1 minus phi 2. It doesn't matter. That's just the phase angle.
Yeah, omega t. I mean.
Oh, I think it's because one is moving to the right.
Were you talking about this, the phase angle?
No, I'm talking about omega.
Omega t.
Oh, no, Omega has to do with the direction of the travel.
Okay, so one is.
Here we're focusing on two waves that are starting at the same, well, starting somewhere, and they're traveling to a certain point. You see?
Yeah.
Like that. and we want to see how they combine. So they're traveling in the same direction.
Same direction.
So they both have negative omega t because they're traveling in the same direction. When they're traveling opposite directions, you have to.
Now you might say to yourself, well, can't we say speaker here and then there's another speaker here, and this is traveling this way and this is traveling this way? Well, then what's going to happen then? Then it's they're going to create standing wave.
Okay.
But in that topic, we're more concerning waves that are traveling in the same direction when they're going and meeting a spot.
Okay.
You see?
That makes sense.
Yeah,
Thank
so
you.
they're both negative, yeah. Okay, so here then you're going to have your phi 1 minus phi 2 over 2. And then it's going to be your sine of, then you're going to have kx, 2kx plus phi 1 plus phi 2 over 2. Is that going to change a lot? Then you're going to have here this would be the most general scenario you would have. Sine of kx plus phi 1 plus phi 2 over 2, negative omega t. Then if we want, we could take out the negative here and then change this to, take out the negative, so then this would be, because since cosine is an even function, right? You get cosine of negative x is equal to cosine of x. So take out the negative, so then this would be positive, then change this to negative, which means switch the order of these. Okay, so why is this not a traveling wave, and why do we call it a standing wave? So to make it simple, then we can say, let's assume phi 1 equals phi 2, which equals 0. Just to make it the more simpler version, so we can study what the nature of that wave is, then we can kind of generalize to any. So how do we analyze the properties of that wave?